is by Matt Hastings, and he's going to talk about optimizing strongly interacting fermionic Hamiltonians. Talk is 20 minutes plus maximally 5 minutes questions. We'll see how it goes, and put your questions in the chat so I can pick up on them later at the end of the talk. Go ahead, Matt.
Okay, thank you. Yes, please ask questions. Let me just mention there's also my collaborator, Ryan O'Donnell, has a talk, a live talk on YouTube that you can watch on this subject. And Ryan is a more clear speaker than I am, so you might find that also interesting to watch and maybe give it different perspective. So I'm going to be talking about, it's kind of a fundamental problem for quantum computing. How do you approximate or get the energy approximately of some quantum Hamiltonian? That's one of the main potential applications of a quantum computer. Let me back up a little bit and talk about approximating some classical Hamiltonian. So let's say we have some classical Hamiltonian, and I'll use the notation of qubits that we're used to. So we have some like Hamiltonian H is sum over, say, I and J, some Jij, Zi, Zj, where Z's are some variables that are plus minus 1 and J is some matrix of couplings. How can you approximate the optimum value, say the ground state energy of this Hamiltonian? This is an NP-hard problem to get the energy exactly, but let's say we only want an approximation. Let's just generalize it a little bit. Here you notice that there's 2 factors of H. So we could say this is degree 2. It's quadratic in these classical values. So you might wonder, well, what if it's just linear in these classical values? So H is a sum over like Ji, Zi. Well, this is, of course, completely trivial to do. You just point each spin either up or down, depending upon what the Ji is. This Jij was quadratic, and then there's also a cubic version where you start having some Zi, Zj, Zk, Jij, Jik. So there could be linear, quadratic, cubic, and I'll get back to that in a second. This quadratic occupies a very interesting point. The linear is completely trivial. The quadratic, there are powerful algorithms based on semi-definite programming called like the Gomans-Williamson algorithm and generalizations of that, which are capable of doing a reasonably good approximation. One way to say it in words is that if there's something that's significantly better than random, meaning just assign each Zi plus minus 1 completely at random, in which case the average value of the Hamiltonian is 0. If the optimum is significantly better than random, Gomans-Williamson will find something significantly better than random. It will actually find you a state that's significantly better than random. If you express this in terms of a constraint satisfaction problem, which is where you say instead of these couplings that can be plus minus 1, you have a set of constraints where the constraint is the 2 spins are aligned, or constraint is satisfied if they're anti-aligned. Gomans-Williamson will get a constant factor approximation on the number of constraints that's better than the random one, and believed to be the best possible. So Gomans-Williamson gets this non-trivial approximation for the quadratic. And it does 2 different things. It gives you a certificate that says, okay, the energy is some value here, like the true energy is some value here. It gives you a lower bound certificate, some lower value for the energy that it says it proves rigorously that the energy cannot be less than that. And it gives some rounding to give some true state whose energy is perhaps somewhere above the true one. And this is this constant factor approximation that it gets. When you get to the cubic value, the cubic Hamiltonians, Gomans-Williamson can be, or all known algorithms, can be fooled badly. Its approximation for like, what's the best you can do? There are cubic Hamiltonians where it thinks you can do perfectly. It thinks you can satisfy every constraint, and yet you can hardly do better than random. And so it's believed that there's this huge difference in difficulty. Linear is trivial, quadratic has this non-trivial approximation, but you can do reasonably well, and cubic is just approximating is essentially impossible. Now let's say we want to go to quantum problems. This is QIP, right? So your first thought might be, instead of talking about bits, let's talk about qubits. So you might start looking at a Hamiltonian that has some Zi, Zj terms like that, and then has also perhaps some Xi, Xj terms with some other matrix of couplings, we'll call it Kij, and then perhaps, you could even have more general things that are, why is that not showing up? Sorry, my stylus is having a little trouble here. Some Kij for some Xi, Xj terms, and so on. Maybe you have some Zi, Xj, Yi, Yj, and so on. And this seems like a natural generalization to qubits. There still is necessarily a good constant factor approximation algorithm. The very simple constant factor approximate that does better than random, in the same way that Gomans-Williamson does better than random. The constant factor approximation that does better than random is for every spin, just randomly pick a Pauli operator. For this spin, we're going to use Z. For this one, we're going to use Y. For this one, we're going to use X. Just do it at random. And then you get now some just consider only those terms in the Hamiltonian. So only the terms that involve like Zi, Yi, if I pick Z on this one and Y on that one. And then you're now back to a classical problem. You only involve variables on each spin which commute. One spin is either only Y, only Z, only X. And you can apply the same Gomans-Williamson. And that gives you a constant factor approximation to a fraction of the terms in the Hamiltonian. And so it gets you a non-trivial approximation for the whole Hamiltonian. Maybe not the best you can do, but there is some reasonable approximation you can make for spin problems. For the quadratic ones, the linear spin problems are of course still trivial, and the cubic spin problems are now also going to be completely impossible since the classical cubic problems are completely impossible. So let's go, and that's the subject of this talk, beyond spins to fermions. So let's talk about a Hamiltonian, and I will use Majorana notation for fermions. So instead of using psi dagger and psi, I'm going to use some variables gamma I, and these will be operators so that they square to 1, and gamma I anti-commutes with gamma j if I is not equal to j. So these will be anti-commuting variables. It's just a little bit more convenient notation to phrase it in. They're linear combinations of psi dagger and psi. So if you have a single ordinary fermion with psi dagger and psi, then gamma, you could have two gamma variables, one which is psi dagger plus psi and one which is psi dagger minus psi with some factor of I thrown in there. So now we could look at Hamiltonians in these. We would like a Hamiltonian to be overall bosonic, so we want an even degree in these variables. So we might look at Hamiltonians which are, say, degree 2, gamma I, gamma j, j, I, j. Well, these Hamiltonians can be exactly solved. There's a class of states, Gaussian states. If you had real fermions, not real fermions, complex fermions, if you had psi dagger and psi, and the Hamiltonian was some psi dagger I, psi j, you would have Slater determinants. You would just fill up some energy levels. It's marginally more complicated with these Majorana fermions, but there's a set of states called Gaussian states. You can exactly solve them. So just like linear was trivial for spin degrees of freedom, quadratic is trivial for fermions. Now, what about quartic or degree 6? So you could have Hamiltonians that involve gamma I, well, I'm not sure why my stylus is being a little bit slow, to gamma j, gamma k, gamma L, which are degree 4. I'm really not sure. Sorry, apologize for the stylus. Not all the stuff showing up. J, I, J, K, L. So you could have degree 4 or degree 6. And most of what I'll talk about will be the case of degree 4. It should be apparent that degree 2q for Majoranas is at least as complicated as degree q for that classical problem. Why is that? Well, you can take a pair of Majoranas and think of it as a single spin. Either if the expectation value of like gamma 1, gamma 2, you pair them off. So gamma 1, gamma 2 is one pair, gamma 3, gamma 4 is another pair, gamma 5, gamma 6 is another pair, and so on like that. And then the operator gamma 1, gamma 2 commutes with the operator gamma 3, gamma 4, commutes with the operator gamma 5, gamma 6. So you've got a set of commuting variables. You can think of them as classical variables. So you can encode any classical optimization problem of degree q into some Majorana problem of degree 2q. So the Majorana problem with degree 4 has to be at least as hard as the classical problem of degree 2. So the Majorana problem of degree 6, which is at least as hard as the classical degree 3, is completely intractable. So let's focus on the Majorana problem of degree 4. Now, there's an interesting question, which is, can we get some reasonable classical state? Just like for the classical problem, we would start with this Gomans-Williamson. We would kind of round it to a state, which would then round it to something where it's just each spin is up or down. We might like some kind of approximation for this degree 4 problem and then round it to some kind of state. The most obvious state you might want to round it to is a Gaussian state. So you might say, if you give me a Hamiltonian of this form, H is Ji, Jkl, gamma I, gamma K, gamma L, can you always come up with a Gaussian state that's a reasonable approximation to the ground state energy of the problem? And in some cases you can. In some cases you can. One would be that the Hamiltonian is simply the square of a quadratic Hamiltonian. If you have a quadratic Hamiltonian, it's optimized by a Gaussian. Its square will be optimized by the same Gaussian, and its square will be a quartic Hamiltonian. But there's another interesting case, which is that you simply pick the JIJKL independently at random. Each choice of IJKL will just be chosen to be a Gaussian variable, independent among all the different choices of IJKL, uniformly distributed, identically distributed Gaussians. This model is called the SYK model, Sachdev-Yekitayev model. It's famous in the high energy physics literature. If you look it up, you'll see all kinds of cool stuff about black holes and holography and stuff like that, none of which I'll talk about, but it is interesting to speculate about possible connections. I will use slightly different normalization from the physics literature. I will take this J, which will be this vector of these JIJKL, and I will fix its 2 norm, its L2 norm to be equal to 1. This is a different normalization. And then choosing them randomly, choosing entries randomly. And then with high probability, the energy, the operator norm, in fact, to this Hamiltonian, the ground state energy is going to be of order square root n. I'm not sure why my stylus is not working here. I do apologize for the technical issues. With high probability, the ground state energy is of order square root n, if you have n of these Majorana fermions. I don't know what's going on with the stylus. I might have a hardware issue with my stylus. Maybe the battery is dying or something. So you might ask, that's the ground state energy of the problem. What is the best possible Gaussian state? What is the energy of the best possible Gaussian state? Well, the energy of the best possible Gaussian state, however, is much smaller. It's only of order 1. So the best possible Gaussian state gives a very poor approximation to the true ground state energy. It's actually not particularly hard to show, and this was shown previous to us, that the energy of the best possible Gaussian state is of order 1. What you do is you want to look at the expectation value of this Hamiltonian within some Gaussian state. You can think of this Hamiltonian, which is degree 4, this JIJKL, which is a sort of 4-index tensor, as being a matrix of size n squared by n squared. You kind of group 2 entries into one and 2 entries into another. And then the Gaussian state, the expectation of it in the Gaussian state is actually take some vector, which corresponds to the Gaussian state, take its inner product with that vector, this matrix, and then that vector again. And by bounding the operator norm of this matrix, you can bound the expectation value of a Gaussian state. So Gaussian states do very poorly for the ground state energy of this problem. The question is, can you do better? Well, if you look at these sum of squares methods, one of the results in our paper was to, so I said the true ground state energy is of order square root n. We looked at a question of verification. So we would like an algorithm that if you give me an instance of this SYK model, will in some sense certify that the energy is at most square root n. What does it mean to certify it? If you took an algorithm that just always said, the energy is at most square root n, no matter what the input is, and always just said that, it would be right almost all the time, because with high probability, that is the energy. But that's not what we want with a certification algorithm. We want something that's never wrong. So our certification algorithm has 2 properties. It will either output a proof that the energy is at most square root n, or it will output nothing. It will just say, I give up, I can't do it. And almost all the time, it will actually output a proof. It very rarely gives up. With high probability, it outputs a proof. So it actually is a good certifier for this problem. It usually gives an answer. And whenever it outputs a proof, it's correct. Those are the 2 properties. And this proof is based upon these semi-definite programming methods. What you do is you look at a matrix of expectation values of gamma I, gamma j, gamma k, gamma l. You look at this matrix of possible expectation values, and you impose some constraints. You impose constraints that it's anti-commutes when you flip I and j, and that it's a positive semi-definite matrix. Turns out at that order you get fooled, but it is unable to output proofs. But if you look at higher orders in the approximation, if you look at matrices of 6 of them at a time, gamma I, gamma j, gamma k, gamma l, gamma m, gamma n, it is able to prove, so this is one thing we showed, that if you use these sum of squares methods at degree 6, it's able to, with high probability, it will give a proof that the energy is at most square root n. So with high probability, it certifies upper bounds for this thing. Conversely, you might wonder, can you prove lower bounds? We also came up with a certification algorithm that proves lower bounds for this model in the same sense. Given an instance of the model, most of the time it gives an answer, and when it gives an answer, what it actually outputs is a quantum state. It's a quantum verification algorithm, and that state has an energy at least square root n. So it gives a variational state. It provides a variational state which has at least that energy. Then you can't say it's never wrong, because if the energy of the state is, you have to phase estimate the energy of the state. So it's a slightly different sense. It's wrong with a probability that you can make as small as you want, because you can repeat the phase estimation as much as you want. And the time taken is only logarithmic in the probability that it's small. So the algorithm can be made to be wrong with as low a probability as you want. So you have a reasonable verification algorithm for lower bounds. And the proof of this verification algorithm for lower bounds proceeds by constructing a variational state, which is not a Gaussian state. It's not a Gaussian state, but it's kind of like a Gaussian state. We take this gamma I, gamma j, gamma k, gamma l, and we introduce some new variables. One variable is the gamma I. The other is gamma is sum over j, k, and l, gamma j, gamma k, gamma l, ji, j, k, l. So it's the thing that couples to gamma I. We call this variable tau I. So now the Hamiltonian can be written as gamma I, tau I. It's quadratic in these variables, gamma I, tau I, bilinear in these variables, gamma I, tau I. The tau I are not actually anti-commuting variables anymore. They obey a more complicated anti-commutation relation. But both of our algorithms, our upper bound and lower bound certification algorithm, rely upon the properties of the tau variables. Our upper bound certification algorithm shows that at degree 6 sum of squares, it knows enough about these tau variables to know that they work reasonably like anti-commuting variables, because it can look at the anti-commutator of tau I, tau j. And our lower bound algorithm involves you initially pretend that the tau variables are really honest anti-commuting variables, and then you make some unitary rotation of the Hilbert space, which turns them into the things that they actually are, and you show that you don't make too big an error on there. So we have these upper bounds and lower bound algorithms. We have a number of different results of the paper. I've only kind of touched on some of what we've done. One possible direction I'm excited about is whether these algorithms could be useful for more practical problems rather than this artificially constructed family, which is particularly interesting because in some sense, most entangled. If you, here's a problem where Gaussian states do badly. You might wonder, the energy of this Hamiltonian is of order square root n. You might wonder, well, if you change the JIJKL, what can happen to the energy? Can it become much larger than square root n, for example? And the case where it can become much larger than square root n is the case where all the Hamiltonian is a square of a quadratic Hamiltonian, which is the same as saying that the Hamiltonian is something like gamma 1, gamma 2, plus gamma 3, gamma 4, plus gamma 5, gamma 6, dot, 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 all squared. And so it's easy to optimize this Hamiltonian. And in that case, the energy is of order n for this particular normalization. And you might wonder, could you do even better? Is there any choice of JIJKL that makes the energy of the Hamiltonian even larger than that? And interestingly, we were able to come up with a proof that there is none, that, and this is again based on sum of squares. There's a sum of squares witness that there is no choice of JIJKL that would have an even larger energy than this thing where the Hamiltonian is just like a square of a quadratic. And sort of remarkably to me, this sum of squares witness proceeds by showing that that problem that you might ask, what's the choice of JIJKL with given L2 norm on the J that optimizes the largest value of H, is basically the same as finding the Lovász theta function, which is an interesting thing studied in graph theory, invented by Lovász for studying certain communication problems. And it boils down to computing the Lovász theta function of a certain graph. So it's kind of remarkable to me that there's these connections between like SYK model, which relates to black holes, and this quartic Hamiltonian, and then these properties of the Lovász theta function. So well, in general, the Lovász theta function, these are STP relaxations. It gives you some upper bound on what the energy actually could be. And in this case, we're able to show that the energy is actually achieved by that. So one of our open questions in general is like, well, we have a large list of open questions. So just to close with them, are there interesting approximations that can be made for the SYK model at degree 6? Our algorithms give upper and lower bounds, but they are no longer tied up to constant factors from what's believed to be true. They're pretty far away. So degree 6, we don't get much done. Are there ways in which for this low-Vash theta function upper bound, cases in which it may or may not be tight. Well, read the list of paper, and I guess I'm out of time for all the other open questions. So let me just take questions now. Thanks.
Thanks, Matt, for a very fascinating talk. Very much a whirlwind of some of the results in this paper. Right now, I don't see a question, but maybe I can ask a question. So this SYK model has all the fermions, everybody talks to everybody, right? And so, yes. So is it known that if you have a Hamiltonian where every Majorana term is interacting in order one other term, with order one other Majorana fermions, that you get a constant approximation ratio with Gaussian states? Or can you comment on this?
I think this is a fascinating question you get to. I mean, this is fully connected. People have studied a little bit sparse versions of the SYK like you talked about. And I think this is a fascinating question. One, could there be models simply where Gaussian states don't do well? And I think it may be a potential, just like there's this NLTS conjecture that people have been looking at, whether there are states of spin Hamiltonians where there is no low energy state that is not highly entangled. You might ask, are there states of Fermionic Hamiltonians where there is no low energy state that is not highly entangled? And there you might even ask for more than it's not a Gaussian, but it's not even a Gaussian followed by some low depth quantum circuit on the Majoranas. And, I think what you asked touch on that, like maybe, you might start looking at low degree instances of this. And I think it's a very fascinating question. Like the kind of the cool thing about this model is it's a random model that forces any reasonable state to be highly entangled in the random case. It can't be, but whether there could be sparse things that have the same property, I think is a fascinating question.
Okay, thanks, Matt. Maybe I can throw in a last question and then we have to wrap up. So what if you, you can do, you can map this fermionic stuff to qubits, right? Now the set of Gaussian states doesn't get mapped maybe nicely, but would you not also, can you say, sometimes you'd like to map it onto a local Hamiltonian. This is not always possible. It's possible if you have a lattice or something, and this is not at all like that. But have you explored that, or is there any known results about that by mapping it to qubits with some of these mappings, Jordan Wigner or other stuff, you could get also insight?
Yeah, so certainly if you map this to qubits, it will become some incredibly complicated qubit Hamiltonian, partly because it's fully connected. So if you apply some, say, Jordan Wigner transformation, a fermion operator will map to like a Pauli X multiplied by some enormous string of Pauli Z's, for example.
So you think there's no sort of K local Hamiltonian that would map onto if you would, have only order one extra qubits or something?
I don't think. I mean, and part of the reason I don't think is that, here there's just these incredibly entangled states is the only way to make a good approximation. And I think for qubits, there's usually going to be some, not so entangled state that has a reasonable approximation. If you simply follow this trick of, we'll just pick like randomly for each qubit, we're only going to keep the terms on this basis on this qubit. So I think that sort of already tells you there can't be a good local approximation.
Okay, yeah, thanks. All right, I think we have to wrap up. I'm going to stop the live stream, and if you want to talk more with Matt about this